Good day, and welcome to wscc Math 2110 Statistics. We're continuing Chapter 2 in the text, and we're now talking about how to graphically display the data. I'm going to talk about some different types of graphs used, and talk a little bit, start to get into the basic shapes that a distribution can take. One of the key things about a graph is it should be able to stand alone without the original data. So for that reason, it is important that you have the title and labels for both axes. When appropriate, you need a legend, a source, date, anything somebody might need to have included in order to interpret the data needs to be there. Just a moment. Okay, so let's start off with Let's start off with pie charts. Pie chart shows how large each category is compared to the whole. It can be used primarily for qualitative or categorical data. So, pie chart uses the relative frequencies to divide the pie into different sized wedges. The central angle of each wedge is calculated by multiplying 360 degrees by the relative frequency of each class and rounding to the nearest whole degree. So, as an example of pie charts, here is one of the most accurate pie charts ever made. We have pie I have eaten, pie I have not yet eaten. And now I'm getting hungry. Let's get back to the... Come on. There we go. I know we've all seen pie charts before at some point. Okay, so let's look at our example here. We've got student housing. Housing specifically students in a statistics class. We've got 5 in a sorority or frat house, 9 in a house, 20 in apartments, and 15 in the dorms. So let's calculate the size of each wedge in the pie chart to the nearest whole degree. Okay, they've added this up for us nicely. There's 49 total students. So remember, we want the frequency divided by the total to get the relative frequency. They've very nicely given us frequencies here. That's the count of students in the overall group that were in an apartment. Right? Then we take that frequency and that relative frequency and multiply it by 360, round to the nearest degree, and that should give us the central angle measure, which then we could, if we wanted to graph it by hand, get a protractor out and carefully make the graph. So take a minute and calculate those, and unpause when you're ready to move on. Okay, so here are our relative frequency numbers, rounded to the nearest whole percentage, and they add up to 100. Then here are our central angle measurements, which is, there's 360 degrees in a whole circle, so this is 41% of a whole circle is about 147 degrees. Be another way to think about this if that's easier for you. Or if you just need to remember the formula and work off that, that's fine too. At the end, though, it should add up to 360 degrees. If it doesn't, then you've probably rounded something wrong somewhere. Okay. If we were to take those angle values and build the pie chart, it would look like this. Usually you have different colors for each section. Then you need to have a legend, that's this part here, that tells you what the colors correspond to in your data. We can also have bar graphs. Represents the amount of data in each category as the length or height of a bar. It can be horizontal or vertical. It doesn't really matter. A Pareto chart is a specific type of bar graph in which the bars appear in order from the largest to the smallest. It's usually used with categorical data, nominal data, something where the order is not important to the data interpretation. So if I were doing die rolls or something, it doesn't, and I rolled more sixes than twos, it doesn't matter which I present first. So I could do it in a Pareto chart and I can see the order of what I saw in my data, and that wouldn't interfere with the interpretation of the data. If I had something that was time-based and I did it by order of frequency, then everything would be all messed up because I'd have different times mixed up weird on the axis. We can also create side-by-side bar graphs where you compare the same categories for different groups, and there will be examples of these in a moment. And a stacked bar graph where you can get the contribution from one group and the contribution from another group, so you can, if you want to do a little bit of subtraction, you can get the individual contribution from each group, and you also get the overall contribution to that category very easily. It's a dense, efficient way of displaying things. So let's look at an example of creating a bar graph. So again, we've got our housing types for students in the statistics course. This time we've got them ordered from highest to smallest. This is the same data set we had the pie chart of. So they're nicely in order for us. We can make a Pareto chart, which they've done here. So you can see we've got 20, the height of the bar matches the frequency. 15 in the dorms, 9 in the house, and 5 in fraternities or sororities. So the height of the bar, or if it was, if we tilted it sideways, the length of the bar corresponds to the frequency. Okay, so here's our next example. They want us to create a Pareto chart if it's appropriate for the following data. So the first thought is this appropriate? Does the order matter? Will it be harder to interpret if I change the order of which classroom I present first? No, it's not. So it makes sense to rearrange this from the largest down to the smallest. So like so. Number of fundraiser items sold. So this is already the frequency of fundraiser items sold here. So we've got frequencies. Why don't you go ahead and take a minute and roughly sketch out this this chart, and unpause when you're ready to move on. Okay, the book chose to create this horizontally instead of vertically like the previous one had been. Kind of makes sense given the screen size and ratio of things. It's probably a better use of space to do it this way. That's really the only difference, is what's going to fit in the space you're making this better. It doesn't matter if it's horizontal or vertical. Okay, so let's look at a side-by-side bar graph now. So we've got our our housing types group, and we've added a second data set to that. So there's our first data set that we've been using up till now, and here's a second data set. So in a side-by-side bar graph for each category, we're going to have one data set and the second data set right next to each other with a little gap in between. So we'd have, for example, in apartments, we'd have the 20 apartment bar, then right next to it there'd be a 30 apartment bar, and then we're going to need a legend. So go ahead and take a minute and sketch that out, and unpause when you're ready to proceed. So it comes out looking like this. We've got sample A, the sample we've been working with in blue, and sample B, the second sample, is in green now, next to it. Right? So you can see within each class, we've got the two sample sets right next to each other. We can't really, I mean, it doesn't make sense to present this so much as a Pareto chart anymore, because even though sample A is listed from highest to lowest, sample B is not. It doesn't quite match anymore in that way. The next exercise is to create a stacked bar graph for this. So if you were to imagine these green bars sitting on top of the blue bars, so you had a stack. So the apartment would be, you'd have a 20 unit high blue section and a 13 unit high green section on top of it, ending at 33. And you do that for each section. So take a moment and set that up, and then unpause when you're ready to move on. And we have this. So one of the things that gives us really is an easy way to see what the overall trend. It's easy to see that we've got a lot more students living in the dorms overall. This one you could take and have a stacked Pareto chart. Really, we could order it from highest down to lowest based on the stacked data. But what this really does is it does make it easy to see what the overall trend is. And if you're wanting to, you can still go, let's see, I've got 39 total here, 15 from group A, so group B is 39 minus 15 is 24? Yeah, 24. So that data is still there if you want to do just a little bit of math to calculate it. Okay, so the next type of bar graph we want to talk about is a histogram, more precisely called a frequency histogram, usually just referred to as histogram, and it is a bar graph of the frequency distribution of quantitative data. Then there's also relative frequency histograms, which the heights of the bars are the relative frequency instead of the frequency of each class. Visually, they should be identical. If your height of 40 is 10%, it's going to be, all the relative heights will be the same if you're presenting them as frequencies or as relative frequencies. So a histogram is a bar graph of a frequency distribution. The horizontal axis is a real number line, and the width of the bars represents the class width from the frequency table, and it should be uniform. The bars in the histogram should touch, and the height of each bar represents the frequency. So if we were to look at our 3D price data and frequency distribution from our 3D TV price data from section 2.1, we've got that here. We've got our class boundaries and our midpoint and frequencies. If we were to plot this as a histogram, we'd have bar charts where each bar is touching with these heights, and it would end up looking like this. We'd label those according to that midpoint. Well, you could label it according to the midpoint, or you could label each class boundary. That would work too. So that's labeled as midpoints. That's labeled as class boundaries. We can do the same thing with the relative frequency distribution. So there's a portion of that, well, there's the first portion of the data, there's the next portion. Let's move on. So it ends up looking like this. If we flip back a few slides, you can see that looks the same as that. If you weren't looking closely, or if you weren't paying attention to notice that my y-axis has changed, you might think they're the exact same graph. And that's the way it should be with the frequency versus relative frequency histograms. They should look the same. Frequency polygon is a version, you could consider it a version of a frequency histogram. You basically take that frequency histogram and put a point at the midpoint of each class and draw a straight line in between those. And there, you have it. Essentially, there is some additives. You take those, you add an extra class at the beginning and end with a value of 0. So if we were to take our 3D TV data that I do not have on these slides to show you quickly, and plot it, and then add that extra class at the beginning and end, we end up with this, where there's our extra class at the beginning and our extra class at the end, and our data points that are assigned to the middle. So you can see in the slightly lighter color, we've got the class boundaries here. The midpoints are darker. Then when we draw a straight line in between each, we end up with this polygon. The next iteration of that is called an ogive, which is, it's essentially a frequency polygon reporting cumulative frequencies. Now in this case, it's created the same way. In this case, you only add the extra class at the beginning. You don't add the extra class at the end. It should add up to whatever your number of data points is. So if we were to take our 3D TV data here with those class boundaries, and again, we're going to be, with the ogive, as with the frequency polygon, we're plotting this at the midpoint, so you're going to need to calculate the midpoints. Take a minute and create the ogive. You're basically plotting the cumulative frequency instead of the frequency. You do note that they have added this extra class with a frequency of 0 at the beginning and not added an extra one at the end. And you end up with something like this. It is important that you label the y-axis appropriately, that this is the cumulative number of TVs, so that somebody isn't misled by your graph. You can see that's 2. We've got 7 that are priced, from here to here now. 12 that are priced from here to here, so it's cumulative. Next way to visually present data that they talk about in the book is a stem and leaf plot. Um, while I've personally not seen these outside of a math class yet, that doesn't mean there's not a use for them somewhere that I just don't know, because it's, it's clearly important because it's important enough to include. I just haven't seen the use for it. Um, it's kind of similar to a histogram in that it gives you an idea of the frequency of things in each bin in each class. I may slip and call them bins because when you're building these histogram in Excel, they refer to the classes as the bin range. Um, and so if you think of it as a bin or a bucket, that you're counting how many data points fit in each bucket. That's another way to think about the classes. Um, and that's the terminology that's used inside Excel when you're building histograms in there. Okay, so one of the characteristics of a stem and leaf plot is that it retains the original data. Um, so the portion that is called, they refer to as a leaf, is usually the very last digit in each data value, and the stems are the remaining portion. Um, and you need a legend or key to help with the interpretation. Okay, so a stem and leaf plot is going to look a lot like a small table with two columns, one on the left for stems and one on the right for leaves. Um, each stem is usually listed only once. So you put stems down in the left column in numerical order, and you put each leaf next to its stem. You list each leaf as many times as it occurs. So if you've got duplicates, you put the duplicates in. Um, please try to make sure they're lined up in straight columns so that the size gets to be visually accurate. And then you create a key. If you want to put them in order, you create an ordered stem and leaf plot. All right. I'm not going to pause too long for you to do this example because without seeing a stem and leaf plot, it's a little hard to visualize what this is. I have a hard time visualizing based on their text here what it is. So if we've got this list of ACT scores, and we want to create a stem and leaf plot, not an ordered one, just a stem and leaf plot of these ACT scores from college freshmen. So we've got two digits. This first digit is going to be our stem, so we've got a 1, 2, 3. Do we have anything besides 1, 2, or 3? No. And then the last digit is going to be our leaves. So there's our stems and our leaves. So you note that the leaves are aligned in even columns so that we get a visual indication of that would basically correspond to the length of bar in a histogram just by looking at it. So the key here is 1 in the stems and 8 in the leaves is 18. So we've got 18, 19, 18, 18, and 17 as the values that fit in this class. Right, so if I look back at my value, I've got 18, 18, 19, 18, 17, and so all of my original data is there, and I can extract it from the stem and leaf plot if I need to. But at the same time, I can visually see the histogram type distribution. If I took that and put it in order, like so, then we'd have a nice ordered stem and leaf plot. Okay, so now that you've seen one, you should go ahead and create one from this data. There's a few questions I wish I knew a way to show two slides at the same time, but I don't. So here, I will just read the questions and leave the data here. And you can pause as necessary in between each question. So first thing you'll want to know is what are the smallest and largest salaries recorded? Right, so for example, I've got 51 there. It looks like 51,500 might be the largest. Quick scan. I'm not sure the smallest. There's 42,500. Yeah, so these are our smallest and largest right here, I think, without spending more time looking. Which salary appears most often? Um, how many salaries were in the range 41? Oh, sorry, we're using the stem and leaf plot to answer these questions, not using these questions to create them. Okay, so we want to create a stem and leaf plot from this. You can. One of the things you'll note is, we created the last one with using the last digit. The last digit of everything here is 0. If we create the stem and leaf plot using that, it's going to be pretty useless, right? So what we're going to want to do is use these last 3 digits, because that's the part that's going to be changing. So you probably want, for example, the stem to be 51 and the leaf to be 5, and then in the key something to indicate that 51 comma or 51 5 is 51,500. So each leaf is in the hundreds. Okay. These are the questions we want to answer. We will come back to that. Hopefully you guys remember significant digits from the previous math course. So basically what we've done by looking at just the hundreds place is we're looking at the last significant digit in each data point. The zeros between that and the decimal place are just they're placeholders that don't have a whole lot of extra meaning. So that gives us this plot. Hopefully you took a moment to create that. I forgot to pause before I switched it over. So you can see we've got 40,700, 40,900. There appear to be nothing in that range. Right. 47,700, 49,000 even, 50,000 even, 50,700, etc. Okay, so on to those questions. I want you to keep your copy of this chart in front of you for a minute and go back to these questions. Take a minute, answer the questions, and unpause when you're ready to proceed, and we'll move on. Okay, smallest salary was 40,700, largest was 51,500. Pretty easy to see from this plot. This is an ordered stem and leaf plot they produced here, so that makes it even easier. Oops. 46,300 appears twice. Nothing else does. So again, you look at that. There we've got repeated 3s there. No other repeated numbers in that leaves column, so it's fairly easy to spot those, especially if it's an ordered chart. We have no salaries in that range, so there's no leaf corresponding to it. Okay. If we count the leaves in a given group, that gives us the frequency number, and we can see where the most salaries are. We could also see it just by visually looking. There's our most salaries right there. Oh, okay. They're looking at a larger range here. This range. Okay. Um, okay, the next one is a dot plot, and again, this is not one I've seen. The largest difference between it and a stem and leaf plot is it's given there's no grouping, so it's an ungrouped frequency, and the points are plotted as dots. Um, so this works best with with data where there are going to be discrete values. So like if I was rolling a dice and recording my results there on a number line, I would put a dot in like so each time I rolled whatever value. So again, you're getting that histogram frequency type data in a slightly different format, in a way that the original data is still there and not grouped somehow. A line graph is data measurements over time. So in the horizontal axis, you've got time, and the vertical axis is the variable being measured. So, if I wanted to look at average daily temperatures over the year, a line graph would be a fine way to do it. You see these for things like stock market price trends and things like that. They're pretty common. Straight line connects each point. So, for example, we're looking at consumer price index over several years. There's our data. If we wanted to create a line graph of this data, we've got a CPI every 10 years. So we would plot the year, put a point on the in the graph corresponding to the height, the y-axis, and connect them. So for consumer price index with this data, you can see there's the Great Depression. Prices started going down on things. Climbed back up after World War II, and then sometime in the 70s it started skyrocketing. Wow. And we end up with that. Okay, so let's summarize these. We've got pie charts, pie I've eaten, pie I haven't eaten, pie I might be willing to share, but I doubt it. Bar graphs, Pareto charts, a sorted bar graph, a side-by-side bar graph. We've got two groups next to each other for easy comparison. And a stacked bar graph, the groups are stacked into the categories, so it makes it easier to see the category total while still being able to see the group differences. Histogram is a bar graph of a frequency distribution. We will be dealing with histograms more. That is what a lot of statistics gets built on top of. And frequency polygons, which is basically your histogram converted into a line. Ogive, which is that line except as a cumulative frequency instead of frequency for each individual thing. Stem and leaf plots, dot plots, and line graphs. Okay. That is it for, there we go, this one, and enjoy your break.